Okay, chapter 8 is all about deformation mechanisms. How, when you deform things, what's actually happening at the individual microstructure or crystal structure that allows them to deform. And on a normal year, we would watch some sweet YouTube videos on deformation, how blacksmiths make different things and talk about the deformation mechanisms there. But I will get in trouble if I post their videos on YouTube, so I can't. So maybe we'll do it during office hours. I can walk through some of these. All right. Let's talk about deformation of metals, right? In metals, plastic deformation is permanent, and anytime that you get permanent deformation, that involves breaking and reforming of bonds. It's not like elastic deformation where you just stretch that bond. You're actually breaking it and forming new ones, right? And that usually involves the motion of dislocations. We've talked about dislocations, edge and screw dislocations, right? If you get those to move in a material, you can achieve deformation. Here's how it works. An edge dislocation is going to travel perpendicular to its line and parallel to the applied force. So here's our edge dislocation. That's this example over here, right? So if you're shearing it this way and that way, the edge dislocation itself travels in that same direction. And the end result is that extra half plane of atom slowly inches its way through the material, like it is down here. See, here's our extra half plane of atom. As you shear this material, it moves, right? Breaking bonds as it goes until it pops out at the end. And so you've deformed your crystal by that thing moving its way through the material. A screw dislocation is actually different. When you apply the exact same shear stresses to it, right, the dislocation actually moves that way, but it pops out the same way at the end. You get the same deformation in either scenario. So either screws or edge dislocations can both achieve the same deformation, but they move perpendicular to one another. Okay? And at the end, if it does create it, then you've annihilated your dislocation if it reaches the end of the material and deforms. You now have there's no defect in either of these scenarios. You've gotten rid of the edge dislocation and the screw dislocation, okay? So these often annihilate at things like grain boundaries, okay? Something that's important to note is dislocation density, or the total number of dislocations, right, in a material. We usually calculate this by figuring out what's the dislocation length, the total length, per unit volume, or equivalently, you could say the number, not the length, but the number of dislocations per unit area in some random section. Okay, so therefore you can either do millimeters per millimeter cubed, that would be distance per volume, or you can just do number per area squared. Same difference, right? Now, in a really pure material where you've gotten rid of the dislocations, it could be as low as 1,000 of these per square millimeter, right? Still quite a lot, right? In a square millimeter, you still have 1,000 dislocations, and that's on the low end. And now if you are like a blacksmith and you're pounding on a piece of metal, you're going to be introducing lots and lots of dislocations, right? Every time that you smack that, you're potentially breaking lots of these bonds and allowing them to get disjointed and, well, dislocated, imperfected, right? So it can be as high as 1 billion to 10 billion dislocations per square millimeter. Just bonkers. The blacksmith then takes that and they put it back in a furnace and they heat treat it, and that will reduce the dislocation density all the way down to maybe 1 million per square millimeter, right? Now, ceramics, on the other hand, have way fewer dislocations. They are not nearly as tolerant as metals to dislocations, something like 100 to maybe 10,000 per square millimeter, right? In a really high purity electronic single crystal, right, where they grow these single crystals of silicon, you can get it as low as 1 or less defect of these dislocations per square millimeter, which is bonkers. Okay, but that's dislocations. And again, as you are pounding on a material, you're creating dislocations, and as these travel all the way through, that allows you to get plastic deformation at the end.